Go ahead.
Hey, thank you for the introduction. So hello, my name is Piotr Dulian. I work at this faculty and the Center of New Technologies. And I work with Rafał Dymkowicz-Dobrzański, and here I will present you the package, numerical package we developed in our team, which provides a set of useful tools for quantum metrology. Okay, so in quantum metrology, we are usually interested in a scenario where we have some physical process parameterized by some real parameter theta. We call this process parameterized channel or probe channel. And we are interested in measuring this parameter theta as precise as possible. More formally, we are interested in finding finding an optimal input state we can plug into this channel, and then optimal measurement, which will give us the optimal precision of measurement. And even more interesting scenario is when we have multiple channel uses, because then we can start to implement various strategies to improve the precision of our measurement. So the simple case would be here with just when we just repeat our measurement n times, we gather all the data and estimate the parameter based on our results. But we can do much more than that. For example, we can consider a large entangled state and act on the state with all our channels simultaneously or in parallel. That's why I call this strategy parallel strategy. And then we can measure collectively the whole output. And because of entanglement and additional correlations that appear because of it, we can improve our precision. The other strategy we can consider is a strategy where we put in between our channels some control operations that can, for example, mitigate or correct errors that occurred because of the noise. And these control operations additionally communicate with each other with this additional. Do I have a pointer? Oh. Okay. Does it work?
Yeah. Plug in this.
Oh.
And then it should.
Unless it's not USB.
Oh, it's USB.
It is.
Yeah. Should work now.
You should press and hold, and now move. Exactly.
Ah, thank you.
Okay.
Okay. So there is this additional space called ancilla, which allows control operations to communicate with each other. And you can notice that if this ancilla space is large enough, for example, it consists of, assuming this, let's say this channel is a qubit channel, and we have ancilla which has n qubits, then by putting as control operators appropriate swap gates, we can basically simulate with this strategy the parallel strategy. However, in a case when the dimension of this additional space is limited, it is not clear which strategy would be better. And we can also consider some hybrid strategies when we combine parallel and adaptive with each other. We can consider a simple case like this one or something more complicated. We can be also interested in a scenario where there is an additional environment space to which we don't have an access, but our channels interact with the space and they become correlated because of it. Or we can consider a case when in our adaptive strategy, ancilla space is actually noisy and there is some noise model we want to apply on it. So basically the message is that there are many, basically infinitely many various strategies we might want to consider. And what our package does is provides a function that takes your strategy, defined by a user, find optimal values of input states and control operations and measurement. And also it assesses its quality by computing the quantity called quantum Fisher information, which I will introduce in a moment. And yeah, the important message here is that it can do so for arbitrary, causally definite strategy. It has good performance for a large number of channels. For example, we can go to n equal 100, which is much better than other solutions existing in the market. It is also, at least I hope, easy to use. I will try to convince you to this in a moment. And there are also some additional features, for example, functions that provide upper bounds on quantum Fisher information, which can help us in our computations. OK, so I've already explained what is QMetro. Now I will dive into the theory behind it and the algorithm. And then I will show you how to use it in practice. OK, so let's start by defining what is quantum Fisher information. So let's go back to the scenario from the very beginning with just one quantum channel. And then notice that after we apply this channel parameterized by theta, the output state also depends on theta. So the probabilities of different outcomes of measurements, they depend on theta. And what we want to do is to estimate the value of our parameter. To do that, we use estimator function. And we say that our precision is good when the variance of this estimator function is small. So basically, we want to make it as small as possible and find optimal values of rho 0 and measurement to minimize this value. And by Kramer-Rao bound, we know that this variance is bounded from below by reciprocal of the quantity called quantum Fisher information. This quantity can be defined as a maximization of some function I call pre-QFI function. This is maybe a bit unorthodox definition for those of you who know different definitions. So basically, we can compute quantum Fisher information by maximizing this pre-QFI function by finding its maximal value. OK? And the message here, the main message is that the bigger is the QFI, the better is the estimation protocol. OK? So how can we maximize pre-QFI function? To do that, we use iterative seesaw optimization, which works in the following way. First, we notice that this pre-QFI function is concave in each of its arguments, but separately. So if we keep one of our arguments constant, then the function, the other argument, is concave. And what this gives us is that the concave maximization problem is a well-known problem with many known solutions and implementations of that solutions. So we can solve the problem when one argument is constant. We can find the maximal value for the optimal value for the other. Okay. But how to maximize it over both of its arguments? The idea here is that we start at some random value of these two arguments. Then we keep one of them constant. So for example, here we start at 0.0. We keep rho 0 constant. And then we find maximal value of L for this rho 0. And then we switch. Then we start to look for the optimal value of rho 0 for this L. And we do that interchangeably up to a point when our optimization converges. So up to a moment when pre-QFI function stops changing. And in a case, we consider a more complicated strategy than the single channel use.
Sorry, but you are aware that such a strategy is not provably convergent?
Yes, yes.
So you, in principle, you can get a lower bound.
A suboptimal result.
Which will be a lower bound.
Yes.
On the QFI.
On the QFI. Okay. But okay,
It's still good.
I will show you results that it actually usually it converges to the optimal value, but yes, we don't have a proof for that. And okay, so for more complicated strategy, we need to generalize pre-QFI function to a function not only of input state and the L matrix, but also to a function of all control operations. And then we basically do the same as before, which is we set all arguments except one to some constant value, and we optimize over this one argument. And then we change to another argument, and we do that repeatedly up to the point our algorithm converges. OK, so that's basically the whole theory behind it. Now I will show you how one can use it in practice. And first I want to tell you that there are two main modes of operations for this package. One is, let's say, very simple and basic, where user can just use one of the already implemented functions. So for example, there's a function that computes QFI for adaptive strategy, and you just need to specify what is your channel, what is the number of users, and compute QFI. And there's also a more advanced approach where the user can create their own strategy, build it by hand, and then plug it into an optimization function and optimize it. And this requires a little bit more knowledge, but it's also more powerful. OK, so let's start with the basic approach. I will choose some example of parameterized channel. Here I chose perpendicular amplitude damping. This is a channel that squeezes the whole, this is a qubit channel that squeezes the whole block sphere towards the minus state. And then it rotates the whole thing around the z-axis. And this rotation depends on the parameter theta, which we want to measure. OK? So first, to use this channel in our computations, we need to instantiate an object of a param channel class. And we can do that in various of ways. So for example, we can do that using our Krauss operators and their derivatives in the parameter theta. Here you can see the code. But we can also use the Choi matrix of this channel, if this is more convenient. Or in some cases, like this one, there's already a function that just takes the parameter that specifies this noise and gives you the parameterized channel. And in case you have a continuous time regime, you can also instantiate your channel from the Lindbladian and its derivative. Okay, so there are multiple ways.
So then the last one integrates numerically, or because you have parameter time equal 1?
Yeah.
So uses some solver, or?
Actually,
not really numerically, because it's enough to take exponent of matrix.
yeah, it's just an exponentiation. So.
So L does not depend on time.
Yes.
Yes.
Okay.
Yeah. OK, and then if we, let's say, want to use, for example, the adaptive strategy, we just need to choose appropriate function. This one is called ISS TNet adaptive QFI. We need to plug into it the channel, specify the number of channels we want to use, and specify the dimension of the ancilla. OK, so now I will try to show you how this looks in practice. OK. OK. So here you see in the first line, we define our channel using this implemented function. We set n to 3 and ancilla to the dimension of the ancilla to 1, which basically means that there's no ancilla. And then we plug it into the function and wait until it converges. OK, it gave us some number. Maybe it's a random number. Let's check. So we can actually plot how the value of pre-QFI function changes with each iteration. OK, and you see it took it, like, I think, 16 iterations to converge. It starts by increasing very quickly, and then it saturates. Okay? And then let's check what happens if we increase the size of the ancilla dimension. This will take a little bit longer, but still it should be a few seconds. Okay, it gave us another number. And then when we compare those two results, then we see that for bigger ancilla, we got higher value of quantum feature information. So now we can wonder whether if we increase the dimension again, whether we can get something even better or not. So we could just perform a computation for even bigger dimension. But the other thing we can do is we can use a function that computes upper bound for quantum feature information, and it computes it for all possible ancilla sizes. And this one we actually can prove it works. Okay? And then when we plot the bound, we see that actually for two-dimensional ancilla, we saturate the upper bound, so we got the optimal value. Okay? Yeah. So let's go back to the presentation, and let's consider this advanced mode. I will consider a very simple variation on the adaptive strategy. So everything is basically the same. The one thing we want to change is that we no longer want to perform optimization over the input state. We want to set it to some constant value. And we want to just find optimal values of control operations and measurement. Okay? Okay, so before I explain how to do this, let me introduce what is a tensor network formalism. In this formalism, we represent tensors as nodes of a graph. And indices of this tensor are represented as edges. And then when we want to contract two tensors, we just connect their edge, their appropriate edge. And this represents the contraction as shown here. Okay? So to compute QFI for arbitrary strategy, what we need to do is to first decide on a strategy. This is something we have already done. Then we would need to build a tensor network representing this strategy. And in this tensor network, we need to set, or maybe denote, that some of the tensors should stay constant, that they shouldn't change during the optimization. Here I colored them to blue. And that some of them are variable tensors, so they should be optimized over. And when we have such a network, we just need to plug it into a function ISS_opt and run it. Okay, so the biggest mystery is here how to create this tensor network. And to do this, QMetro provides, in a sense, symbolic programming way of defining your strategy, your tensor network. So it's a little bit like in, let's say, Mathematica, which is symbolic. So there are constant tensors, which are similar to, let's say, numbers in Mathematica, like 1, 2, 3, 4, 5. There are variable tensors, which are like x, y, z in Mathematica. And when you, let's say, write in Mathematica 2 times 3, you get 6. But when you write 2 times x, you get 2x, right? So when you multiply two numbers, you get another number. When you multiply number and a variable, you get an expression. Okay? So expression here are represented by tensor networks, which are just connected tensors. And there are also tensors which have defined which have defined derivative over the measured parameter. So these are the tensors that we will use to represent our channel, our parameterized channel. Okay, so let's go one by one over our types of tensors. So there are constant tensors. They have some value which needs to be provided during the instantiation. They don't change during the optimization. And when you contract it with other tensor, you get another constant tensor. Okay? There are also variable tensors again, which don't need to be, which don't have any value. You don't need to specify it when you create such a tensor, and they will change during optimization. And when you contract such a tensor with a constant tensor, let's say, then you can't get like a new constant tensor because y doesn't have any numbers, it doesn't have any value, so you need to get expression, namely the tensor network here. Okay, and this tensor network for outside to other tensors looks just like any other tensor, which have some legs, shape, and so on, but it has some internal structure. Okay, and then parametrized tensor, it also has a set value, and since it also doesn't change during the optimization process, recall that these tensors are meant to represent our parametrized channels. So we don't want them to change during the optimization. So they actually are a type of constant tensor. I know this might be a little bit counterintuitive, that something parametrized is called constant, but the name constant is from the point of view of the optimization process. And how they are implemented is that they are just a pairs, or maybe not exactly pairs, but something like a pair of two constant tensors, where one represents the value of this tensor at some point, let's say theta equals 0, and the other represents its derivative at this point. Okay? And then when you want to contract two parametrized tensors, then the result is computed using Leibniz rule. Okay, so let's make one more live presentation.
So maybe a question. When you contract tensors, they need to have same dimension. So in your code, you will fix the dimension of all the legs to be the same throughout the network? Or
No.
People say that channels are connected via higher dimension or lower dimension?
How it is implemented is very similar to these diagrams. Basically, you need to give each leg a name, and this name is connected to the dimension, so these dimensions can be completely different. And then when you contract two tensors, if they have indices with the same name, then they will contract. So that's how it is done. So you can have different dimensions. And
so apart from the network, you could write numbers on each leg, specifying the dimension.
yes, basically you can do something like that.
Then for the same architecture, I can compare different dimensions, because this is okay.
Yes. It just, if you want to contract two indices, they have to have the same dimension, right? Okay. Okay, so to recall, what we want to do is to optimize adaptive strategy, where we keep input state constant, and we will set it to just 0, 0 state for ancilla of dimension 2, so to a separable pure state.
Can I have a clarification about this adaptive strategy? So would you allow in such a case that your subsequent variable operations are based on a measurement of some ancilla, or is the measurement of the MPN?
For that, we can give you a lower bound on I think, classical Fisher information, but generally, no.
Okay. So for this case, no. Just
Not really. Because Well, quantum Fisher information can be understood as a classical Fisher information optimized over all possible measurements. So if you want to specify some kind of measurement, then you can't really look for quantum Fisher information. You want to optimize classical Fisher information. And then formulas are a bit ugly, and well, we don't know how to do that.
No, but the question of Michał is, like, I could also compute quantum Fisher information, but I restrict pi to have a tensor problem. The pi will be a local measurement. This you cannot do, I understand. Put constraints on the set of measurements.
Yeah, for that we can only give lower bound.
What do you mean you can give lower bounds?
Lower bound on, let's say, well, because you could, here let's say, you could just make two nodes for measurement and don't connect them with each other. So then the result of the optimization would be a lower bound on classical Fisher information for a separable measurement. But it won't give you classical Fisher information for...
An upper bound on the classical, because you optimize over measurements.
Yeah, we optimize, we go from, we try to maximize. And in this case, we will be not able to attain the real maximum.
Okay, so we get a lower bound on upper bound.
No, we get a lower bound on Fisher information.
Here, yeah?
What?
You always get an upper bound because you are calculating quantum Fisher.
Yes.
In this sense, yeah. So we get lower bound and upper bound. Yeah, in this sense, yes.
And I understand then you will get what Michał wants, no? Because you will be able to just measure the ancilla. But okay, but if it converges, it's good. Yeah. So if you see that it converges and somehow have intuition that it's true,
Then yeah.
it can be useful.
Yes, it can be useful, for sure. Okay, so we want to, I explained that. So let's look at the practical example. Okay, so here's the code. You don't need to understand everything, of course. Just note that, for example, for const tensors, we have such a constructor. You then need to specify some value for it. For channels, we have param tensor, and then you need to specify, for example, Choi matrix and its derivative. And there are also variable tensors. And for them, for example, you need to specify what type of variable is it. So here, it is specified that this is a measurement and not an operation, for example, right? And then when you want to contract these tensors, you can just use star symbol. And by that, you create tensor network. And then you just plug this tensor network into ISS opt, and you run it. Hooray, we got something. And then we can compare it to our previous results. And okay, what we got is that we got something a little bit worse than if we would optimize over input state as expected. But we got something a little bit better if we didn't have ancilla at all. Okay, so...
But sorry, but can you interpret this result? Because if you optimize over all C0, if you go back to the plot, no? To your scheme, optimizing over all C0, you're optimizing also unitaries that act on the ancilla, right? I can write any C0 as 1 times, right? I can push that unitary into row 0.
You can't make a 0 and time.
So you can make, it's a separable state. This is what you're saying.
It was separable state.
Okay, so if you change that state to a Bell state, will that converge? I don't know if it
We can check. And that's a nice thing about it.
Sorry, everyone.
No, it's actually a good question.
Yep. that means that that your tensor network is not realizing all possible C's. No?
Doesn't have to, because maybe fully entangled state is not optimal.
Okay. Or the tensor network is not representing all states. So this is the question I wanted to ask. How you guys will... I think here the tensor network is of dimension 2. Each bond is of dimension 2. Because there are two things in your code, right? There's what state you choose. Also, does your tensor network faithfully represent all possible operations?
Okay, so in this case, it does. So here we have...
Bond dimension 2, right?
No. We have ancilla 2. So it's, in a sense, bond dimension of, let's say, these control operators.
Exactly.
But I think that what you're talking about...
No, so if I have an ancilla... Tensor is a representation of a density matrix. So if ancilla is 2, then the dimension is 4, right? 2 qubits. And then it should be 4 squared, so you have 16 parameters. So I'm saying in this case, I think you covered all.
Yes.
But if you had bigger systems, there are two things. You could, the tensor network would be faithfully representing all the states, or the state is suboptimal. So I think I agree with Staszek that here the tensor network covers all C's, but you will not be able to, do you agree with me? Tensor network, unless you make the ancilla d squared, the bond dimension d squared, it's not a full representation.
But you're talking about bond dimension of this state?
On the contractions you make, no?
But you're talking about contractions that are here, or that are inside this state?
You could also do the connection between C0 and C1. You could also make a stupid thing. You should kill this by making here at bond dimension 1.
Yes.
This will not be good, no? Even though
this would be as if you didn't have ancilla at all, right?
Oh, you still have, because C0 would have input.
Yeah, okay. Yeah, but not between those two.
Exactly. So I'm saying there's 2 degrees of freedom you can play with.
Yes. And in a case, maybe when we are talking already about it, in case you have a state that acts on many spaces, so it would be exponentially large, you can actually also represent it as a tensor network. This is called matrix product state, where there is an, let's say, artificial index that connects these elements. And the bigger this index is, the more correlations you can have. But for example, for small, if this index was small, then you would get like an optimization over some subset of possible input states here. But this would be much more efficient, of course. Okay, so that's basically it. This result is not yet published and this package, but if you're interested, then I encourage you to contact me. And, well, there's also a bibliography.
Thanks for the talk. We had plenty of discussions, but perhaps now there are questions. New topics, new questions for discussion.
So I have one. So you have an upper bound of quantum Fisher. There are also upper bounds on quantum Fisher, like by variance. So if your CISO provides a lower bound, can I also compute an upper bound and at least have some, type of...
Some estimation, yes.
Some kind of sandwich type.
Mm-hmm.
Have you thought of doing that? Like rather than QFI...
That's exactly what Piotr showed, right, in this figure. Because he showed a black line, which is upper bound, and these dots are lower bounds.
Yes, but this upper bound is, I understand, some kind of QFI bound, like we know from Gauss operator, like metrology.
This alpha,
beta stuff, yes. Yes, but then I'm thinking of something that you, for example, fix this POVM like we discussed.
Mm-hmm.
Then you don't want, this upper bound will be loose, no?
Mm-hmm.
But then you could do some just upper bound. You had a slide on what is Fisher, no? And this is this pre-QFI. Right? You have a pre-QFI. the one you showed how to optimize, no? So I'm just saying that maybe take something which is an upper bound on Fisher, and then do the seesaw as well, no?
For the upper bound.
Yes, at least, okay. Now will it converge? I don't know, but at least you'll have a sandwich inequality. So for example, if you go one slide back, or two, this one, yes? You can upper bound Fisher as a variance with respect to effective Hamiltonian. No? Basically, my question is, could you not create sandwich inequalities? Do you understand what I mean?
I don't really see how to do it.
Yeah, I don't see how to do it, but I think I understand what you would like to do, but
You could, okay. Because maybe you can use those right logarithmic derivative Fisher, and for them those methods should work, yeah, and they would give you an upper bound.
Yes. For instance, okay, there is a plethora of this upper bound.
but then we would need to perform minimization. Yeah, maybe.
Yeah, you're right. But then still you'll do maximization, so you'll get a lower bound and upper bound, but at least it'll be something can be tighter than the black line.
Yeah, maybe. Yeah, that's an interesting idea.
Because you want to do something for fixed method, right?
Or something that the upper bounds are so general, for fixed strategies. If you start playing with sequential, this hybrid, you call it hybrid, no?
So you want to add some constraint?
Exactly, still, and then the black line will be too loose, no? Because the example you gave us was kind of easy, no? The black line is tight. No?
Yeah, here we know analytically that it is tight.
So, simpler questions. When you do the optimization over many Cs, this is like a multi-dimensional seesaw that you kind of go one by one in many dimensions, or is it some kind of collective optimization? How does it work?
No, for each C separately.
Okay.
Yeah.
And the other simple question, the pre-QFI, is it really just also the classical Fisher for the specific rho and L, or any other, or why do you call it pre-QFI? And because like fundamentally quantum Fisher is classical Fisher optimized over stuff, right?
Yes. So, but there's also this definition of quantum Fisher with symmetric logarithmic. Yes.
Yeah.
So, for optimal values of rho 0 and L, this L would become this SLD.
Okay.
Here in this example.
All right.
Yes.
All right.
It's more complicated because like this is real quantum Fisher, but for every row that you obtain in this seesaw algorithm, yeah?
Okay.
Because it works like that you maximize this over row at some point, yeah? And then calculate SLD.
But I think
Yes.
it's more trivial. So this expression for optimal, the first d rho L is equal to rho L squared.
Mhm.
So this expression is 2x minus x, so you get x. But this is only true if L is the SLD.
Okay.
Yes.
So really
yes.
the trick is that a minimum of a parabola, it's a minimum of a parabola. That's it,
Sure.
right? Rather, you take a function which is quadratic and write it as a minimum of a parabola. That's
All right. Any other simple questions? Complicated ones? That's all. We have plenty of discussion. Thank you.